The first thing to go was the sound. One moment, the Pratt & Whitney R-2800 Double Wasp was a symphony of controlled violence, its 18 cylinders converting high-octane fuel into 2,000 horsepower of earth-shaking thunder. The next, it was a discordant clatter of protesting metal, a death rattle that echoed through the armored cockpit. A plume of black oil, thick and viscous, vomited from the cowling, instantly smearing the windscreen and transforming the pilot's view of the cold gray Pacific into an abstract nightmare. He knew with the chilling certainty that only a combat pilot can possess that his war, and perhaps his life, was now measured in seconds. He was flying a dead machine. The F4U Corsair, the bent-wing bird that Imperial Japanese pilots had come to call the Whistling Death, was now just a 3-ton glider, and the only runway in sight was 1,000 miles of unforgiving ocean. He fought the controls, his gloved hands moving with the instinct born of hundreds of hours of training. His voice, strained but steady, crackled over the radio, broadcasting his position, a final desperate pinprick of hope on an empty map. He jettisoned the canopy, the sudden roar of the wind, and the freezing spray, a violent shock to the senses. As the fighter's nose dropped and the stall warning horn began its mournful shriek, he pulled the release handle, ejecting from the cockpit and tumbling into the void. The parachute opened with a violent crack, a sudden brutal deceleration that felt like being hit by a truck. Below him, his Corsair, spiraled down, a wounded hawk falling from the sky. It hit the water, not with a splash but with a concussive boom, the impact tearing the massive wings from the fuselage as the ocean swallowed one of America's most advanced weapons. Within hours, as the American pilot bobbed in his life raft, praying for a rescue that might never come, a different kind of vessel converged on the floating wreckage. Japanese patrol boats, their crews alert and efficient, had been vectored to the site. What they recovered from those cold waters would become one of the most significant intelligence opportunities of the war's final, desperate months. For nearly 3 years, Japanese pilots had faced this American fighter in the skies, over the Solomon Islands, Rabaul, the Philippines, and now the home islands themselves. They had learned to respect its speed, its firepower, and its seemingly indestructible construction. They had seen Zeros, the pride of the Imperial Navy, disintegrate under the concentrated fire of its 6 heavy machine guns. They had watched it absorb 20mm cannon shells that would have torn their own aircraft to pieces, only to see it limp away, trailing smoke, but still flying. But never before had they possessed an intact example to examine in detail, to measure, to test, and to finally understand how far behind their own nation had fallen. The story of Japan's encounter with the F4U Corsair is not merely a tale of captured aircraft. It is the chronicle of a nation's painful technological awakening, the moment when Japan's finest aviation specialists confronted the full terrifying magnitude of American industrial and engineering superiority. Through the systematic autopsy of this one fighter, they would discover truths about manufacturing, precision materials, science, and design philosophy that would shatter every assumption they held about their own capabilities and confirm their deepest fears about their enemies. The news of the recovery reached the Yokosuka Naval Air Technical Arsenal, south of Tokyo, like an electric shock. Here, in secured workshops and laboratories, Japan's best aeronautical minds had spent the war engaged in a desperate race against time, trying to reverse engineer Allied technology from battlefield scraps. They had worked with shattered engine blocks pulled from jungle crash sites, with twisted wing fragments recovered from downed bombers, with pilot reports that were often more legend than fact. It was like trying to understand a lion by examining a single claw. Now, they had the entire beast. Kenji Tanaka, a senior engineer who had helped refine the final designs of the legendary A6M0, felt a knot tighten in his stomach. For years, he had read the combat reports with a mixture of professional pride and growing dread. Pride in the skill of Japanese pilots who, in the early days, could use the Zero's unparalleled agility to run circles around American fighters. But dread at the recurring descriptions of this new American naval fighter. The reports were disturbingly consistent. It could not be outdived. It could not be caught in a climb. It absorbed damage like a flying battleship, and its firepower was, in the words of one surviving ace, like flying through a buzzsaw. Tanaka and his colleagues had theorized, they had built mock-ups based on fragmented evidence, but theory was no substitute for reality. The arrival of the salvaged Corsair at Yokosuka was a moment of supreme professional importance. It was a chance to unlock the secrets that were systematically destroying the Imperial Japanese Navy's air arm. Yet, beneath the engineering curiosity, there was a deeper, more personal fear. Tanaka had dedicated his life to the pursuit of aeronautical perfection, as defined by the Japanese ethos, elegance, efficiency, and a symbiotic relationship between pilot and machine. He feared that the American machine, now being carefully transported to his facility under heavy guard, represented a different, more brutal kind of perfection. A perfection born not of elegance, but of overwhelming, unimaginable industrial power. As the flatbed truck carrying the tarp-shrouded fuselage rolled through the gates of the top-secret analysis hangar, a hush fell over the assembled engineers. They were surgeons about to perform an autopsy on an alien creature. They knew its capabilities, but they did not understand its anatomy, its soul. They were about to peel back the skin of their most feared adversary and look directly into the heart of the arsenal of democracy. What they would find there would change them and their understanding of modern warfare forever. The challenge they faced was immense, but so was the potential reward. Unlocking the Corsair's secrets could provide the key to developing countermeasures, new tactics, or even a new generation of Japanese fighters that could finally meet the Americans on equal terms. It was a faint hope in the darkening days of 1945, with B-29 seconds beginning to burn the heart out of Japan's cities, but it was a hope nonetheless. And for an engineer like Tanaka, it was the only hope that mattered. The truth was waiting for him cold and silent under that canvas. If you want to be there with Tanaka and his team as they pull back that tarp and begin to unravel the manufacturing secrets that both amazed and terrified them, make sure you're subscribed to this channel and have notifications turned on. The journey into the heart of this captured legend is just beginning, and you won't want to miss what they find inside. The story of the machine that now lay in pieces on the floor of the Yokosuka hangar did not begin in the chaos of combat, but in the quiet, methodical world of a Connecticut design office in 1938. The world was on a knife's edge, and the United States Navy, watching the storm clouds gather over Europe and Asia, knew its current generation of carrier fighters was dangerously obsolete. The Grumman F-3F biplane, a tough but slow aircraft, was still the fleet's frontline defense. The new monoplanes, like the Brewster Buffalo, were proving to be disappointments. The Navy needed a leap, a quantum jump in performance that would guarantee air superiority over the oceans for the next decade. The Bureau of Aeronautics issued a request for proposal that at the time seemed almost like science fiction. They wanted a shipboard fighter capable of exceeding 400 miles per hour in level flight, a speed no American fighter had yet achieved. But the demand wasn't just for raw speed. It had to have a range of 1,000 miles, carry a heavy armament of machine guns and cannon, be rugged enough to withstand the brutal, controlled crashes that constituted carrier landings, and still possess a low enough stall speed to operate safely from a pitching flight deck. It was a list of contradictions, a demand for a heavyweight boxer with the agility of a ballet dancer. Most manufacturers looked at the specifications and proposed incremental improvements on existing designs. But at Chance-Vought Aircraft, a division of United Aircraft Corporation, a Georgian-born engineer named Rex Beazle saw an opportunity for revolution. Beazle was not a man who thought in small steps. He was a visionary who understood that to achieve a revolutionary result, you had to start with a revolutionary premise. He and his team, including the brilliant chief engineer Igor Sikorsky, who would later become famous for his helicopters, made a decision that would dictate every single bolt, rivet, and wire of the aircraft to come. They decided not to design a fighter and then find an engine for it. They would do the opposite. They would find the most powerful, most monstrous aircraft engine available in the world, and then they would build a fighter around it. Their choice was the Pratt & Whitney R-2800 Double Wasp. It was less an engine and more a force of nature, an 18-cylinder air-cooled two-row radial engine that displaced 2,800 cubic inches, nearly 46 liters, and in its initial form produced a staggering 2,000 horsepower. It was an engine designed for medium bombers and transport aircraft, not nimble fighters. It was huge, heavy, and insatiably thirsty for fuel and air. This single decision represented a fundamentally American approach to engineering, one that Kenji Tanaka and his colleagues at Yokosuka were only now beginning to comprehend. It was a philosophy of brute force, of solving problems not with finesse but with overwhelming power. If you need more speed, don't just refine the aerodynamics, install a bigger engine. If you need more firepower, don't just add another cannon. Design a structure strong enough to carry 6 heavy machine guns with thousands of rounds of ammunition. Beazle himself famously admitted to his design team, "It will be a dinosaur, but it will be a dinosaur with good proportions." This was the conceptual DNA of the Corsair. It was never intended to be graceful in the way a Spitfire or a Zero was graceful. It was designed to be an instrument of overwhelming technological violence, a platform for the R-2800 engine that could deliver its apocalyptic power to a target. Every other consideration was secondary. The fuselage was designed with the minimum possible frontal area to wrap tightly around the massive engine, giving it its distinctive barrel-chested appearance. The cockpit was placed far aft behind the long fuel tanks needed to feed the Double Wasp, which unfortunately resulted in terrible forward visibility for the pilot during takeoff and landing, a flaw that would plague the aircraft for years. But it was a necessary compromise to achieve the required range. The structure had to be immensely strong, not just to handle the engine's torque and vibration, but to serve as a stable gun platform and withstand the G-forces of high-speed combat. This resulted in an aircraft that was, by the standards of the day, grotesquely overweight. An empty F4U weighed over 9,000 pounds, nearly twice the weight of a Japanese Zero. But as American engineers understood and Japanese engineers were about to learn, with enough power, even a brick could fly. And the R-2800 provided more than enough power. The prototype, designated the XF4U, first flew on the 29th of May, 1940. It was a stunning, almost brutalist piece of design. On October 1st of that year, it made history, screaming across the Connecticut sky at an average speed of 405 miles per hour, becoming the first single-engine American fighter to break the 400-mile-per-hour barrier. The press hailed it as a world beater, a marvel of American ingenuity. But for the engineers at Vought, the celebration was short-lived. That first flight had revealed a host of problems, the most significant of which was born directly from their decision to use the R-2800 engine, a choice that would create a monumental engineering problem of its own, a problem that would give the Corsair its most famous and most misunderstood feature. Back in the Yokosuka hangar, Kenji Tanaka stared at the detached wing of the Corsair, a massive, strangely shaped structure resting on wooden cradles. The dimensions alone were imposing, but it was the shape that held his attention, the distinctive inverted gull wing. For years, Japanese intelligence had speculated on its purpose. Was it for stability in a dive? Was it a complex, aerodynamic trick to improve lift? The theories were numerous, but none were conclusive. Now, with the physical evidence before him, Tanaka was beginning to understand that the wing was not the starting point of the design, but the solution to a problem. A problem created by the Corsair's Heart of Thunder, the R-2800 engine. An engine that produces 2,000 horsepower needs a way to translate that rotational energy into thrust. In the world of propeller-driven aircraft, that means a propeller, and in the case of the Corsair, it meant the largest propeller ever fitted to a fighter aircraft. The Hamilton Standard hydromatic propeller, designed for the Corsair, was a three-bladed behemoth measuring a staggering 13 feet and 4 inches in diameter. Its blades, broad and paddle-like, were designed to bite into the air to claw the 9,000-pound aircraft forward with brutal efficiency. But this colossal size created an immediate and seemingly insurmountable engineering paradox. The landing gear of a carrier-based aircraft had to be incredibly strong to absorb the punishment of repeated deck landings, but it also had to be relatively short and compact to retract cleanly into the wings and fuselage. A long, spindly landing gear, while providing propeller clearance, would be a structural weak point prone to collapse under the violent forces of a carrier landing. The math was unforgiving. To provide the necessary 18 inches of clearance between the propeller tips and the ground, a conventional straight-winged aircraft would require landing gear so long and heavy that it would have crippled the design, adding hundreds of pounds of weight and compromising the structural integrity of the wing. Rex Beazle and his team were trapped. Their choice of the R-2800 engine, the very foundation of the Corsair's performance, had led them to a propeller so large it made a conventional design impossible. They could have chosen a smaller engine, a less efficient propeller, but that would have meant sacrificing the speed and power the Navy had demanded. It would have been a compromise, and the Corsair was a design of no compromises. The solution they devised was a stroke of counterintuitive genius. Instead of making the landing gear longer, they would bring the ground closer to the airplane. They designed a wing that dropped sharply downwards from the fuselage at a steep anhedral angle before leveling out into a conventional wing section. This created the distinctive M shape when viewed from the front. The main landing gear was mounted at the lowest point of this gull, at the joint where the wing bent upwards. This configuration allowed the landing gear legs to be short, stout, and immensely strong, plugging directly into the most robust part of the wing spar, yet the downward bend of the inner wing section provided all the ground clearance the massive propeller needed. It was an elegant solution to a brute force problem. It was also, as Kenji Tanaka now realized, an absolute nightmare to manufacture. A conventional straight wing is a relatively simple structure, but the Corsair's wing was a complex piece of three-dimensional geometry. The main spar, the load-bearing heart of the wing, had to be forged with multiple complex bends while maintaining its structural integrity. The ribs had to change shape and angle precisely along the wingspan. The outer skin had to be formed over these compound curves without wrinkling or creating aerodynamic drag. It required a level of tooling, jigging, and quality control that Tanaka knew with a sinking feeling was beyond the capabilities of Japan's wartime industry. His engineers could design such a wing on paper, but turning that design into thousands of identical, reliable production units was another matter entirely. The wing held other secrets. The deep anhedral of the intersection where it met the fuselage created an almost perfect 90-degree angle, which, as Vaught's wind tunnel test had shown, dramatically reduced aerodynamic interference drag, allowing for a smoother airflow and contributing to the Corsair's high speed. Furthermore, the outer wing panels folded upwards hydraulically for carrier storage, a complex and heavy mechanism, but one that was engineered with a robustness that impressed the Japanese team. They examined the massive hydraulic actuators, the precision-machined locking pins, the heavy-duty hinges. Everything was over-engineered, built to withstand not just use, but abuse. This was not the delicate, lightweight construction they were accustomed to. This was industrial-grade power and precision. The Corsair's wing was a microcosm of American engineering philosophy: confront a physical limitation with overwhelming power, solve the resulting problems with sophisticated and complex but brilliantly effective engineering, and then build it with a robustness that bordered on indestructible. As Tanaka's team began to draft their initial findings on the wing structure, they understood they were looking at more than just a clever design. They were looking at a physical manifestation of an industrial capacity that could afford the complexity, the weight, and the resources to build such a thing not by the dozen, but by the thousand. It was a sobering realization, and it stood in stark contrast to the philosophy that had given Japan its most famous aerial weapon. To truly grasp the shock that the Corsair represented to Kenji Tanaka and his team, one must first understand the machine that was their benchmark for excellence, the Mitsubishi A6M0. The Zero was not merely an aircraft. It was the embodiment of a national engineering philosophy, a martial art in duralumin and steel. When chief designer Jiro Horikoshi began work on the Zero in 1937, he faced a set of challenges diametrically opposed to those of Rex Beazle. The Imperial Japanese Navy demanded extreme range to escort bombers on deep penetration missions over China and unparalleled maneuverability to dominate any dogfight. But Horikoshi had to achieve this without access to a high-powered engine. The engines available from Japanese industry were reliable but relatively underpowered compared to their American and European counterparts. There would be no 2,000 horsepower Double Wasp to solve his problems. Horikoshi's only path to victory was through a ruthless, fanatical pursuit of lightness. Every single component of the Zero was designed, scrutinized, and redesigned to shave off every possible gram of weight. The airframe was constructed from a new top-secret aluminum alloy called Extra Super Duralumin, developed by Sumitomo Metal, which was lighter and stronger than standard alloys. But this was just the beginning. Horikoshi's engineers drilled holes in structural members wherever they would not compromise strength, creating a skeletal structure that was incredibly light, yet surprisingly rigid. They dispensed with armor plating for the pilot. They omitted self-sealing fuel tanks, a decision that would later prove catastrophic as it made the Zero tragically prone to catching fire when hit. There was no room for redundancy, no margin for excess. The Zero was an exercise in minimalist perfection. The result was a masterpiece. An empty A6M20 weighed just 3,700 pounds, less than half the weight of the Corsair. With its low wing loading and exquisitely balanced controls, it could outturn any Allied fighter in the world. In the hands of a skilled pilot, it was a scalpel capable of acrobatic feats that seemed to defy the laws of physics. In the early years of the Pacific War, from Pearl Harbor to the Dutch East Indies, the Zero was invincible. It swept aside the outdated American P-42s and Brewster Buffaloes with contemptuous ease. American pilots trained in tactics that emphasized turning dogfights were slaughtered. They would try to follow a Zero in a turn, only to find the Japanese fighter effortlessly sliding onto their tail, its two 20mm cannons and two 7.7mm machine guns spitting fire. The legend of the Zero's invincibility was born a legend that terrified Allied pilots and fueled Japanese national pride. But Kenji Tanaka, who had worked on the Zero's later variants, knew the dark secret behind its success. Its strengths were also its fatal weaknesses. The relentless pursuit of lightness had created an aircraft that was structurally fragile. It could not withstand high-speed dives. Pushing a Zero too fast could literally rip the wings off the fuselage. It could not absorb damage. A few well-placed 50 caliber rounds from an American fighter could shatter its delicate structure or ignite its unprotected fuel tanks. As the war progressed and the Americans introduced new fighters like the Grumman F-6F Hellcat and the Corsair aircraft designed with the exact opposite philosophy, the Zero's shortcomings became tragically apparent. American pilots learned not to turn with the Zero. They used their superior horsepower and structural strength to execute boom and zoom tactics, diving from high altitude at speeds the Zero could not match, making a single devastating firing pass and then using their momentum to climb back to safety. The Zero, once the hunter, had become the hunted. Now, as Tanaka stood before the captured Corsair, the contrast was physically and emotionally overwhelming. Where the Zero was delicate, the Corsair was massive. Where the Zero was a scalpel, the Corsair was a sledgehammer. The Corsair's empty weight was more than the Zero's fully loaded maximum takeoff weight. Its engine produced double the horsepower. Its structure was designed to absorb the very punishment that would cause a Zero to disintegrate. It was the physical embodiment of two irreconcilable doctrines of warfare. One Japanese prioritized the skill and spirit of the individual warrior, providing him with a light, agile weapon that maximized his personal prowess. The other American prioritized overwhelming industrial might, providing its warrior with a heavily armed, heavily protected, and immensely powerful machine designed to annihilate the enemy through sheer technological superiority. Tanaka picked up a single bolt from a tray of components removed from the Corsair's wing root. It was a standard AN Army-Navy bolt, perfectly machined, its threads clean and precise, its plating flawless. He had seen thousands of such bolts, but the ones coming out of Japanese factories in 1945 were different. The steel quality was inconsistent, the plating was often thin or non-existent due to material shortages. The threads were sometimes rough. The Americans, it seemed, could mass-produce even the most mundane components with a level of quality and consistency that Japan could no longer achieve, even for its most critical parts. This single bolt told a more terrifying story than any combat report. It spoke of a vast, unseen industrial ecosystem operating at a level of sophistication his own country could only dream of. The power of the Corsair, he was beginning to realize, didn't just come from its engine. It came from the mines, the foundries, the laboratories, and the factories of a nation that had turned the very science of manufacturing into a weapon of war. The autopsy of the Corsair at Yokosuka was revealing more than just clever design choices. It was exposing the vast hidden foundation of American industrial power. Kenji Tanaka and his engineers were like archaeologists, uncovering a lost civilization, one that had mastered sciences that we're only beginning to understand. The most profound revelations came from an area invisible to a pilot in combat materials, science, and metallurgy. When Tanaka's team subjected samples of the Corsair's main wing spar to spectrographic analysis, the results were sobering. The material was an aluminum alloy of exceptional purity and strength, with precise amounts of copper, magnesium, and manganese. But it wasn't just the chemical composition that was impressive. It was the grain structure of the metal itself. It was uniform and fine-grained evidence of a highly controlled and sophisticated forging process. This was not something that happened by accident. It was the product of a massive, coordinated national effort. That effort had begun years before the war. Companies like Alcoa, the Aluminum Company of America, had invested heavily in research, developing new alloys and production techniques. When the war began, the U.S. government, through the War Production Board, poured billions of dollars into expanding this capacity. Entirely new industrial complexes were built in the Tennessee Valley and the Pacific Northwest, powered by the massive hydroelectric dams of the New Deal. These facilities could produce high-purity aluminum on a scale that dwarfed the entire output of the Axis powers combined. By 1944, the United States was producing more aluminum than the rest of the world put together. But producing the metal was only half the battle. Forging it into the complex load-bearing structures of a modern fighter required another level of industrial might. The Corsair's wing spars, engine mounts, and landing gear components were shaped not by small workshops, but by colossal hydraulic forging presses. Machines like the 15,000-ton press operated by Wyman Gordon in Massachusetts could stamp out massive complex shapes from a single billet of aluminum with incredible precision. These presses, some of them the size of a multi-story building, were national strategic assets. They allowed American designers to create components that were both lighter and stronger than the built-up structures Japanese engineers were forced to use, which were assembled from many smaller riveted pieces. As Tanaka examined the Corsair's main spar, a single beautifully sculpted piece of metal, he compared it, in his mind, to the spar of a late-war Japanese fighter. The Japanese spar was a patchwork, a testament to ingenuity in the face of scarcity, but it was inherently weaker and heavier than its American counterpart. The Americans didn't have to be clever with patchwork solutions because they had solved the problem at its source. They had simply built the machines that could create the perfect part from the beginning. This industrial superiority extended to every material in the Corsair. The steel used in the landing gear, struts, and engine crankshaft was a chrome molybdenum alloy, heat-treated to an incredible toughness and tensile strength. Japan, lacking domestic sources of chromium and molybdenum, had to rely on inferior steel alloys, which meant their components had to be made heavier to achieve the same strength, creating a vicious cycle of weight and underperformance. The bullet-resistant glass in the windscreen was another shock. It was a multi-layered laminate of glass and transparent plastic over 1.5 inches thick. It was optically perfect with no distortion, yet it could stop a 20mm cannon shell. Japanese industry had struggled to produce even simple laminated glass in sufficient quality and quantity. The idea of mass-producing such a complex and flawless piece of optical armor was unthinkable. Even the rubber in the tires and self-sealing fuel tanks told a story. With its access to natural rubber from Southeast Asia, cut off by Japanese conquests, the United States had performed an industrial miracle. The government had funded a massive synthetic rubber program, building 51 new factories from scratch. By 1944, these plants were producing nearly 1 million tons of synthetic rubber a year, more than twice the world's entire pre-war output of natural rubber. The Corsair's fuel tanks were lined with this advanced material designed to swell and seal punctures, giving American pilots a margin of safety that Japanese pilots flying what were essentially flying fuel cans could only dream of. Tanaka realized that he and his team were not just analyzing an aircraft. They were analyzing an entire system, a system that connected the research laboratory, the raw material mine, the hydroelectric dam, the sprawling factory, and the logistical network into a single seamless weapon of production. The Corsair was simply the end product, the sharp, deadly tip of a very, very large spear. This realization was profoundly demoralizing. He and his fellow engineers were brilliant men. They had created the Zero, a world-class aircraft out of limited resources. They had shown incredible ingenuity in the face of constant shortages. But how could ingenuity compete with this? How could a craftsman, no matter how skilled, compete with a fully automated factory? It was like trying to fight a tidal wave with a bucket. The Americans weren't just out-fighting them, they were out-producing, out-inventing, and out-resourcing them on a scale that defied comprehension. The captured Corsair was a testament not just to American engineering, but to a different way of war, a way that Japan could never hope to match. This truth was chilling, but it did not fully explain everything. After all, the Corsair had not been an instant success. Technology, even superior technology, was not always the deciding factor on the battlefield. As the first combat reports of the Corsair had shown, this American Titan had a baptism by fire that was nothing short of a catastrophe. The legend of the Corsair's 1:1 kill ratio, a number that would eventually cement its place in the pantheon of great warplanes, was not written overnight. Its journey from a promising prototype to a feared combat weapon was paved with early failure, pilot, frustration, and blood. For Kenji Tanaka, studying the captured fighter in the relative safety of his Yokosuka lab, this part of the Corsair's history was a crucial piece of the puzzle. It proved that the Americans, for all their industrial might, were not infallible. They could be beaten. They had been beaten. The Corsair's combat debut was scheduled for February 1943. Marine Fighter Squadron VMF-124, the first unit equipped with the new fighter deployed to Henderson Field on Guadalcanal. The pilots were confident, even cocky. They were flying the fastest, most powerful fighter in the Pacific, a machine that, on paper, could outperform the Japanese Zero in nearly every category except slow-speed maneuverability. They believed they were invincible. The Japanese, however, had other plans. They had been fighting in the skies over the Solomon Islands for months. Their pilots were seasoned veterans, their tactics honed by relentless combat. They knew the terrain, they understood the weather, and they respected their enemy enough to never underestimate them. On February 14, 1943, a large American force of B-24 Liberator bombers, escorted by a mixed group of P-38 Lightnings, P-40, Warhawks, and a dozen of the new F4U Corsairs from VMF-124, set out to raid the Japanese shipping and airfields at Kahili on Bougainville Island. It was a major operation designed to assert American air superiority. The Japanese were waiting. Radar operators on their forward bases had tracked the American formation from the moment it took off. A large force of A6M0s climbed to intercept, positioning themselves perfectly high above, and, in the sun, the classic textbook advantage. The American escort fighters flying in a tight defensive formation around the bombers were at a disadvantage. Their commanders were still learning how to best integrate the different types of fighters, each with its own strengths and weaknesses. The Corsair pilots, new to their aircraft and new to combat, were about to receive a brutal education. The Zeros struck with devastating speed and precision. They dove through the American formation, their cannons and machine guns blazing. The American response was confused and disorganized. The P-38 seconds and P-40 seconds, more maneuverable at medium altitudes, tried to engage the Zeros in traditional turning dogfights, a fatal mistake. The Corsair pilots, confident in their superior speed, attempted to chase the diving Zeros, only to find the nimble Japanese fighters easily evading them. The battle quickly devolved into a series of chaotic individual duels, exactly the kind of fight the experienced Japanese pilots excelled at. The results were catastrophic for the Americans. In the swirling melee, 9 American aircraft were shot down, 2 Corsairs, 4 P-38 seconds, 2 B-24 bombers, and a Navy F-4F Wildcat. In return, the Americans managed to shoot down only a single Zero. The engagement was so one-sided, so utterly disastrous, that it became known as the Street Valentine's Day Massacre. For the pilots of VMF-124, it was a humiliating and terrifying introduction to combat. They had flown the best fighter in the world and had been soundly defeated. The Corsair, the great hope of the U.S. Navy and Marine Corps, seemed to be a failure. The news of the massacre sent shockwaves through the American command. Daylight bombing raids were temporarily suspended. An urgent reassessment of tactics and doctrine was ordered. What had gone wrong? The post-mortem analysis revealed a painful truth. Superior technology is worthless if you don't know how to use it. The American pilots had tried to fight a Zeros fight. They had attempted to dogfight, to turn and burn with an aircraft that was designed for that exact purpose. The Corsair, with its heavy weight and high wing loading, simply could not compete in that arena. It was like challenging a master swordsman to a duel with a sledgehammer. The sledgehammer is more powerful, but if you can't land a blow, that power is meaningless. The Corsair's strengths lay elsewhere in its phenomenal rate of climb, its incredible diving speed, its rugged construction, and its overwhelming firepower. It was an energy fighter, a weapon designed to dictate the terms of engagement through the management of speed and altitude. But the pilots hadn't been trained for that. They had been trained in the old ways, and the old ways had gotten them killed. This piece of history was both encouraging and deeply troubling for Kenji Tanaka. It was encouraging because it showed that even a technologically superior enemy could be defeated through better tactics and pilot experience. It affirmed his belief in the spirit of the Japanese warrior. But it was troubling because it revealed something fundamental about the American character, their ability to learn, adapt, and correct their mistakes with brutal speed and efficiency. They had suffered a devastating defeat, but they did not despair. They did not abandon the Corsair. Instead, they analyzed the failure, rewrote the tactical manual, and retrained their pilots. The Street Valentine's Day Massacre was not the end of the Corsair story. It was the violent, bloody beginning of its true education. The Americans were about to learn how to properly wield their sledgehammer, and when they did, the results would be catastrophic for the airmen of the Japanese Empire. Tanaka knew that this adaptability, this relentless data-driven pursuit of improvement, was perhaps an even more dangerous weapon than the Corsair itself. It meant that any advantage Japan gained through tactical brilliance was likely to be temporary, soon to be countered and overwhelmed by an enemy that learned from every drop of its own blood. The ashes of the street, Valentine's Day massacre became the fertile ground for a tactical revolution. In the dusty, coral-strewn airfields of the Solomon Islands, American commanders and pilots, humbled but not broken, went back to the drawing board. They knew the Corsair was not the problem. Their understanding of it was. The man who would famously codify the new way of fighting was Navy Commander James H. Jimmy Thatch, but the principles were discovered and refined in the heat of combat by Marine pilots who had to adapt or die. They stopped thinking about air combat as a graceful, swirling affair of turns and counter-turns. They started thinking about it in terms of physics, mass energy, and velocity. The Zero was a master of turning, of changing direction quickly in the horizontal plane. The Corsair was a master of energy, of converting altitude into speed, and speed back into altitude in the vertical plane. The solution, therefore, was simple in concept, but difficult in execution. Never, ever try to turn with a Zero. The new doctrine became known as boom and zoom, or energy fighting. It was a brutal, efficient, and deeply impersonal way to kill. A Corsair squadron would use the superior performance of the R-2800 engine to gain an altitude advantage, climbing to a perch high above the anticipated battle space, often using cloud cover for concealment. They would wait circling like hawks until they spotted Japanese formations below. Then the attack would begin. The Corsair pilot would roll his aircraft over, point its nose at the earth, and dive. The Corsair's heavy weight and clean aerodynamics, once seen as liabilities, now became its greatest assets. It accelerated in a dive like a freight train going off a cliff, its airframe designed to withstand the stress of carrier landings, easily handling the immense forces. The airspeed indicator would wind past 400, then 450, approaching 500 miles per hour speeds that would cause a fragile Zero to shed its wings. The sound of this dive was terrifying, a high-pitched banshee-like scream caused by air rushing over the wing root's oil cooler inlets, a sound that earned the Corsair its nickname, the Whistling Death. The Japanese pilot below would often have no warning. One moment he was scanning the empty sky, the next his world would erupt in a hailstorm of 50 caliber slugs. The Corsair pilot would line up his target, unleash a short, devastating burst from his 6 heavy machine guns, and then without slowing or turning, would continue his dive passing through the enemy formation at untouchable speed. He would then use the colossal kinetic energy he had built up to execute a zoom climb, converting his speed back into altitude, rocketing back up to his perch to set up for another attack. The Zero pilot, if he survived the first pass, was left with an impossible choice. He could not follow the Corsair in its dive without his own aircraft breaking apart. He could not catch it in its zoom climb as his underpowered engine gasped in the thin air. He was a fencer facing an opponent who refused to duel an opponent who simply struck with the force of a battering ram and then vanished. The psychological impact on Japanese pilots was profound. The sky, which had once been their domain, was now a place of constant vertical threat. They were forced to fly with their heads perpetually craned upwards, searching for the speck in the sun that could mean instant death. Pilots like Marine Second Lieutenant Kenneth A. Walsh of VMF 124 became masters of this new art. Walsh, who had survived the Street Valentine's Day massacre, understood the Corsair's nature. He used its strengths with ruthless precision. On May 13, 1943, less than 3 months after the disastrous debut, he became the first Corsair ace, shooting down 3 Zeros in a single day. He would end the war with 21 confirmed victories, a testament to the lethality of the aircraft when flown correctly. The numbers began to shift dramatically. The kill ratios, once tragically in Japan's favor, began to reverse. By the end of 1943, the Corsair was achieving a kill ratio of over 6 to 1. By the end of the war, that number would climb to a staggering 1 to 1. For every Corsair lost in air-to-air combat, 11 Japanese aircraft were destroyed. This tactical evolution was what Kenji Tanaka had feared most. The Americans had not just built a superior machine, they had developed a superior doctrine to match it. They had turned their fighters' perceived weaknesses, its weight, and lack of maneuverability into decisive strengths. This was a level of tactical and intellectual flexibility that was deeply alarming. It suggested an enemy that was not dogmatic, an enemy that was willing to abandon tradition and ego in the face of hard evidence. The Corsair, therefore, was more than a collection of advanced parts. It was the physical embodiment of a fully integrated combat system. A system that included not just metallurgy and manufacturing, but also pilot training, tactical development, and a relentless cycle of feedback and improvement. The aircraft that lay on his hangar floor was the product of this entire system. To understand it, he couldn't just measure its wings or analyze its engine. He had to dissect the very mind of his enemy. And the first clue, the first piece of the puzzle that his team was about to examine, was one of the most deceptively simple and confusing aspects of the Corsair's design, a feature that seemed to be a throwback to an earlier, more primitive era of aviation. The Yokosuka hangar was a cathedral of controlled chaos. The salvaged Corsair, now cleaned of saltwater and grime, sat under the harsh glare of overhead lights, surrounded by teams of specialists. It had been methodically disassembled, its components laid out on clean canvas tarps, like the artifacts of a technologically advanced alien culture. Kenji Tanaka walked among the pieces, his mind a whirlwind of observation and analysis. The sheer scale of the aircraft was the first impression that struck every engineer who saw it. It was simply big. The barrel-chested fuselage designed to house the R-2800 gave it a pugnacious, powerful stance. The landing gear struts were as thick as a man's arm, designed to absorb thousands of brutal carrier landings. Everything about it screamed strength, durability, and a complete disregard for the concept of lightness that was so central to Japanese design. It felt less like an aircraft and more like a piece of heavy industrial machinery that had been given wings. Tanaka's first detailed examination focused on the wings. He had already understood the brilliant engineering behind the inverted gull wing shape, but now his team was looking at the construction itself. And they found something that at first seemed utterly baffling. While the leading edge of the wing and the central wing box were skinned and stressed aluminum, a large portion of the outer wing panels aft of the main spar was covered in fabric. To the Japanese engineers, this was a profound contradiction. Fabric-covered wings were a feature of biplanes and early-generation monoplanes from the 1932nd. By 1945, virtually every frontline fighter in the world was of all-metal construction. Japan, despite its material shortages, still strove for all-metal designs for their strength and durability. Why would the Americans, with their seemingly unlimited supply of aluminum, resort to such a primitive construction method on their most advanced naval fighter? Was this a sign of weakness, a desperate measure to save strategic materials, or was it something else entirely? The initial assumption among some of the younger engineers was that this was a flaw, a corner that had been cut in the rush of mass production. But Tanaka was not so sure. Nothing else about the aircraft suggested compromise. He ordered a section of the fabric to be carefully removed and analyzed. The results were surprising. This was not simple canvas. It was a high-grade, multi-layered, doped fabric, a material that had been chemically treated to be taut, waterproof, and remarkably strong for its weight. The way it was attached to the wing ribs with precise uniform stitching and reinforcing tapes spoke not of haste, but of a mature and well-understood manufacturing process. The truth Tanaka began to suspect was far more sophisticated than it appeared. The Corsair had been designed between 1938 and 1940, a transitional period in aircraft design. At that time, fabric covering was still a common and accepted practice for non-structural surfaces. The designers at Vought had made a deliberate engineering trade-off. The portion of the wing aft of the main spar carries very little of the primary flight loads. Covering it in metal would add stiffness, but it would also add significant weight. By using fabric, they saved several hundred pounds of weight on the outer wing panels, which improved the aircraft's roll rate and reduced its overall inertia. It was an intelligent allocation of resources, used the high-strength heavy aluminum where it was absolutely needed in the main spar and load-bearing structures, and use a lighter, perfectly adequate material where it was not. This was a profoundly different kind of thinking. Japanese engineering, driven by a culture of perfectionism, might have insisted on an all-metal wing simply for the sake of modernity and uniformity. The Americans, with their pragmatic, results-oriented approach, had asked a different question. What is the most efficient way to solve the problem? The answer in this case was a hybrid construction. This small detail revealed a larger truth about American design philosophy. It was not dogmatic. It was practical, data-driven, and willing to use an old technology if it was the best solution for a specific problem. It was a sign not of weakness, but of immense confidence in their own engineering judgment. This pragmatism was evident everywhere they looked. As the engineers delved deeper into the wing's internal structure, they were struck by the sheer quality of the manufacturing. The ribs were stamped from aluminum sheet with a precision and consistency that was remarkable. Each rib was a perfect mirror of the next, with lightning holes that were cleanly cut and free of burrs. The rivets were perfectly seated, their heads uniform, their spacing exact. In Japanese factories struggling with worn-out tooling, a depleted workforce of skilled labor, and inconsistent raw materials, such uniformity was becoming a distant memory. Late-war Japanese aircraft often showed visible variations from one plane to the next, the result of hand finishing and fitting that was necessary to compensate for imprecise parts. The Corsair, in contrast, was clearly a product of a system that could produce millions of perfectly interchangeable parts. This was the true magic of American mass production. Not just the ability to produce in vast quantities, but to do so with unwavering quality. The captured Corsair wasn't just a single aircraft, it was a representative sample of thousands, just like it, each one built to the same exacting standards. This realization was far more intimidating than the discovery of any single secret weapon. It meant that the enemy's strength was not in a few elite units, but was systemic, embedded in the very fabric of their industrial culture. And as Tanaka's attention turned from the wings to the massive cylinder that had dominated the aircraft's design, from its very inception, he knew he was about to confront the ultimate expression of that industrial power. Of all the components laid out in the Yokosuka hangar, none commanded more reverence or inspired more dread than the Pratt & Whitney R-2800 Double Wasp. It sat on a reinforced engine stand in the center of the room, a masterpiece of mechanical complexity that was both beautiful and terrifying in its power. For Kenji Tanaka and his engine specialists, this was the holy grail. They had seen the performance data in combat reports, they had heard the thundering roar of the engine from afar, but now they could finally lay their hands on it, dissect it, and attempt to comprehend the secrets of its power. The process began with a meticulous external examination. The scale was the first shock. Its 52-inch diameter was enormous, a dense package of cooling fins, magnetos, spark plug wires, and plumbing. But it was the details that told the real story. The cylinders were not simply cast, but were intricate built-up assemblies. The cylinder barrels were machined from single forgings of high-strength steel, while the cylinder heads with their complex cooling fins were cast from aluminum alloy and screwed and shrunk onto the barrels. This two-piece construction allowed for the use of the best material for each part: steel for strength and heat resistance in the barrel, aluminum for lightness and heat dissipation in the head. It was a complex and expensive manufacturing process, but it resulted in a cylinder that was both incredibly strong and efficiently cooled. The Japanese engineers were familiar with this technique, but the precision of the American execution was on another level. The machining of the cooling fins on the cylinder heads was particularly impressive. They were incredibly thin and densely packed, creating a massive surface area for air cooling. Achieving this required specialized multi-axis milling machines and cutting tools that were in short supply in Japan. The result was an engine that could run at extremely high power settings for extended periods without overheating, a critical factor in the long-range operations and grueling combat of the Pacific Theater. As the engineers began the painstaking process of disassembly, their sense of awe only deepened. They removed the propeller reduction gear housing, a complex planetary gear system that allowed the propeller to turn at an optimal slower speed, while the engine crankshaft spun at high RPM. The gears were made of a high chromium steel alloy, hardened and ground to a mirror-like finish. The tolerances were measured in 10,000ths of an inch. Tanaka ran his thumbnail over the surface of a gear tooth. It was perfectly smooth, a testament to a level of grinding and finishing technology that was world-class. Then they came to the engine's core, the crankshaft connecting rods and pistons. The crankshaft was a work of art, a single massive forging of chrome, nickel, molybdenum steel, dynamically balanced to eliminate vibration. Tanaka compared it to the crankshaft of the Nakajima Sakai engine that powered the Zero. The Sakai's crankshaft was excellent, a product of skilled Japanese craftsmanship, but it was smaller, lighter, and could not handle the colossal stresses produced by the R-2800. The American crankshaft was a statement of power, an object that looked like it could have been pulled from a locomotive, yet was machined with the precision of a watchmaker. But the true secret to the R-2800's high-altitude performance lay at the rear of the engine, the two-stage, two-speed supercharger. A supercharger is essentially an air compressor that forces a denser mixture of fuel and air into the cylinders, allowing an engine to produce power in the thin air of high altitudes. Most Japanese engines used a single-stage supercharger, which was effective up to about 2,000 feet, but saw its performance drop off sharply above that. The R-2800 system was far more advanced. It had two impellers, two separate compressors that worked in series. At low altitudes, only the first stage was engaged. As the aircraft climbed past a critical altitude, an automatic barometric control would shift the system into high gear, engaging the second stage. This was like having a transmission for the supercharger, allowing the engine to maintain sea-level power output all the way up to 25,000 feet and beyond. The complexity of this system was mind-boggling. It required intricate internal ducting, a complex gearbox, and high-speed impellers spinning at over 20 revolutions per minute that had to be perfectly balanced. Any flaw in manufacturing would cause the supercharger to tear itself apart. Japanese industry had attempted to develop two-stage superchargers but had been plagued by manufacturing difficulties, inconsistent materials, and reliability problems. The Americans, it seemed, had perfected it and were mass-producing it by the tens of thousands. This was the technological key that allowed American fighters like the Corsair and the Hellcat to own the high-altitude airspace, forcing Japanese fighters to engage them at a decisive energy disadvantage. As the last bolt was removed and the final component of the R-2800 lay on the inspection table, a profound silence fell over Tanaka and his team. They had seen enough. The engine was not the result of a single brilliant invention. It was the culmination of dozens of interconnected technologies, advanced metallurgy, high-precision machining, sophisticated casting and forging, and a deep understanding of thermodynamics and fluid dynamics. It was the product of a mature industrial ecosystem that had spent decades investing in research, development, and tooling. It was a weapon that could not be copied. To replicate the R-2800, Japan would have needed to replicate the entire American industrial base that created it. And that was an impossible task. The engine was the heart of the beast, the source of its power. But an engine, no matter how powerful, is useless without a body. And as Tanaka's teams began to dissect the Corsair's airframe, they would discover a design philosophy so alien to their own, it would force them to question the very definition of a fighter aircraft. The analysis of the R-2800 engine had been a lesson in overwhelming power. The examination of the Corsair's fuselage and cockpit, however, was a lesson in a different and perhaps even more significant American philosophy. As Kenji Tanaka's structural engineers meticulously documented the airframe, they began to notice a pattern of deliberate, systematic reinforcement that went far beyond what was needed for simple flight loads. The cockpit area, in particular, was constructed like a fortress. Behind the pilot's seat, they found a thick plate of hardened steel armor, carefully shaped to protect the pilot's head and torso from attacks from the rear. It weighed over 150 pounds, a staggering amount of dead weight in an aircraft where every ounce is normally scrutinized. In front of the pilot, the windscreen was not a simple piece of plexiglass, but the 1.5-inch thick, multi-layered bullet-resistant panel they had already noted, designed to stop cannon shells. Beneath the pilot and around the engine's vital oil cooler, there were additional armor plates. All told, the Corsair carried over 200 pounds of dedicated armor. To the Japanese engineers steeped in Jiro Horikoshi's philosophy of absolute lightness, this was heresy. It was a direct violation of the fundamental principle that had made the Zero a world beater. In the Zero, the pilot's only protection was his skill and the aircraft's agility. Adding armor was seen as a weakness, a crutch that would degrade the performance that was the pilot's best defense. The Americans, it was clear, had made a completely different calculation. They had designed the Corsair with the explicit assumption that it would be hit in combat. They had accepted the weight penalty of the armor because they had made a strategic decision that the life of the pilot was a resource worth protecting, even at the cost of some performance. The pilot was not an expendable warrior. He was a highly trained, incredibly valuable component of a complex weapons system. To lose a pilot was to lose years of training and investment. To lose the aircraft but save the pilot meant that a skilled veteran could be back in the fight in a new machine within days. This was a cold, pragmatic industrial logic of warfare, and it was deeply unsettling. This philosophy of survivability extended to the fuel system. When the engineers opened up the main fuselage fuel tank, they found it wasn't a simple metal container. It was a complex, multi-layered bladder made of synthetic rubber. The inner layer was designed to dissolve slightly in contact with aviation fuel, creating a sticky sealant. The outer layers were tough and resilient. When a bullet or shell fragment punctured the tank, the fuel would leak out and hit the inner layer, which would swell and flow into the hole, plugging it within seconds. This was the legendary American self-sealing fuel tank. Japan had attempted to develop similar technology, but their efforts were hampered by the lack of high-quality synthetic rubber and the complexity of the manufacturing process. Most Japanese aircraft, including the Zero, went to war with simple, unprotected aluminum fuel tanks. This was the reason they earned the grim nickname "one-shot lighter" from Allied pilots. A single incendiary round hitting a fuel tank was often enough to turn the aircraft into a ball of flame. The Corsair, in contrast, could absorb numerous hits to its fuel tanks and keep flying. It was another layer of protection, another margin of safety that gave the American pilot a chance to survive an encounter that would have been fatal for his Japanese counterpart. Tanaka now understood the combat reports he had read with new clarity. The stories of Corsairs returning to base, riddled with holes, trailing fuel and smoke but still under control, were not exaggerations. They were the direct result of these deliberate design choices. The Americans had built a machine that could take a punch. They had traded the nimble grace of the Zero for the rugged endurance of a heavyweight brawler. The implications were profound. It meant that in any engagement, the American pilot had a significant advantage in survivability. He could afford to be more aggressive, to take more risks, knowing that his aircraft could likely withstand a hit. The Japanese pilot, on the other hand, knew that any hit could be his last. This created a psychological disparity that was just as important as any difference in airspeed or firepower. As the engineers continued their work, they found this philosophy of robustness everywhere. The control systems were a prime example. Instead of lightweight exposed cables, the Corsair used push-pull rods for its primary controls, ailerons, and elevators. These were more durable and less susceptible to being severed by a single lucky shot. The hydraulic lines for the landing gear and wing-folding mechanisms were routed through protected channels. The electrical wiring was of high quality, properly insulated and bundled, reducing the risk of short circuits and fires. Every system seemed to be designed not just to function, but to continue functioning even after sustaining significant damage. It was a revelation. Tanaka and his team had always thought of fighter design as a delicate balancing act between performance, weight, and firepower. The Americans had added a fourth crucial variable to the equation, survivability, and they had achieved it because they had the one thing that made it possible: the immense brute force power of the R-2800 engine, which could haul all this extra weight into the sky and still outperform its lighter opponents. It was a complete, integrated system. The powerful engine made the armor and robust construction possible, and the armor and robust construction allowed the pilot to fully exploit the engine's power in aggressive combat. As Tanaka stood back and looked at the dissected aircraft, a new picture was forming in his mind. This was not a fighter in the way he understood the term. It was a personal, armored fighting vehicle that could fly. And now his team was turning its attention to its weapons, the very teeth of the beast. They were about to analyze the system that had earned the Corsair its fearsome reputation and delivered the final decisive blow in so many aerial encounters. The firepower of an American fighter was something Japanese pilots understood with visceral, terrifying intimacy. They had seen its effects firsthand, watched as comrades' aircraft were torn apart in mid-air by what seemed like a solid stream of projectiles. But for the engineers at Yokosuka, this was their first opportunity to dissect the weapon system itself, to understand the machinery behind the massacre. The Corsair's primary armament consisted of 6 Browning AN M2 50 caliber machine guns, 3 mounted in the outer panel of each wing. On the hangar floor, one of the wing sections was laid open, exposing the 3 guns and their mounts, a compact and deadly installation. The guns themselves were immediately recognizable to the Japanese armorers. The Browning M2 was a classic design, a weapon that had been in service in various forms since the 1932nd. It was not on the surface a technologically revolutionary weapon. But, as with every other aspect of the Corsair, the true American advantage was not in radical invention, but in relentless refinement and industrial-scale perfection. When Tanaka's team disassembled one of the Browning machine guns, they were struck by its quality. The receiver was machined from a solid block of steel. The The barrel was made of a high-quality chrome vanadium alloy, rifled with exceptional precision, and designed for quick changes in the field to prevent overheating. Every moving part, the bolt, the extractor, the firing pin was hardened and polished, operating with a smoothness that spoke of a mature and flawless manufacturing process. American companies like Colt High Standard and the Frigidaire division of General Motors were producing these weapons not by the thousand, but by the million, with a level of interchangeability and reliability that was the envy of the world. Apart from a gun made in a Frigidaire plant in Ohio, would fit perfectly into a gun made by Colt in Connecticut. This was the power of standardized mass production, and it ensured that the guns on the front lines were uniformly excellent. But the guns were only part of the system. What truly shocked the Japanese engineers was the sheer quantity of ammunition the Corsair carried. They opened the ammunition bays in the wing and found massive metal boxes, each feeding one of the guns. The 4 inboard guns were provisioned with 400 rounds each, while the 2 outboard guns carried 375 rounds each. The total was a staggering 2,350 rounds of 50 caliber ammunition. To put this in perspective, the A6M0 carried just 120 rounds for its 2 20mm cannons. That was its primary hitting power. It also carried 1,000 rounds for its 2 7mm machine guns, but these rifle-caliber bullets were largely ineffective against the armor and rugged construction of American fighters. The Zero pilot had perhaps 10 seconds of effective firing time with his cannons before he was out of ammunition. The Corsair pilot, on the other hand, could fire his guns continuously for over 20 seconds, an eternity in a dogfight. This massive ammunition load meant the American pilot could be prodigal with his fire. He could engage multiple targets. He could use long bursts to walk his fire onto an enemy. He could fire speculative shots to force an enemy to break off an attack. He was not constrained by the ammunition anxiety that constantly plagued his Japanese counterpart. This was not a tactical advantage. It was a logistical one, a weapon born from a nation that could afford to produce and ship billions of rounds of ammunition across an ocean. The ammunition itself was another revelation. The Japanese team analyzed the cartridges from the Corsair's ammo boxes. They found a sophisticated mix of ammunition types loaded in a specific pattern to maximize destructive effect. Typically a mix of armor-piercing, AP, incendiary 1, and tracer T rounds. The armor-piercing rounds could punch through the engine blocks and light armor of Japanese aircraft. The incendiary rounds were designed to ignite fuel tanks and fabric surfaces. The tracers helped the pilot aim and had a secondary psychological effect on the enemy. The quality was once again superb. The brass casings were flawless, the propellant was consistent, and the projectiles were perfectly formed. It was another product of an industrial base that prioritized quality control at every stage. The entire armament system was engineered for reliability. The ammunition was fed to the guns via heavy-duty steel chutes designed to prevent jamming, even under high G-forces. The guns were electrically heated by the aircraft's powerful generator to prevent the mechanisms from freezing at the cold temperatures of high altitude. The spent cartridges were not just dumped overboard, they were collected and ejected through dedicated chutes, preventing them from damaging the aircraft's skin. It was a complete, well-thought-out system designed for one purpose: to put a massive volume of reliable, lethal fire on a target. Tanaka did the math. The 6 guns, each firing at a rate of approximately 800 rounds per minute, produced a combined rate of fire of 4,800 rounds per minute, or 80 rounds per second. The 50 caliber projectile itself was a formidable weapon, a heavy slug of lead and steel traveling at nearly 3,000 feet per second. When a Japanese aircraft flew into the cone of fire from a Corsair, it was not being hit by a few lucky shots. It was flying into a solid wall of metal, a veritable cloud of destruction that tore through aluminum skin, shattered canopies, severed control cables, and ignited fuel. Now, Tanaka understood why the combat reports had described Zeros simply disintegrating. It wasn't an exaggeration. They were being shredded by a volume of fire that their delicate airframes were never designed to withstand. This was the American solution to aerial gunnery. It wasn't about the surgical precision of a single cannon shell. It was about overwhelming the target with such a massive quantity of projectiles that destruction was a statistical certainty. It was brutal, efficient, and horrifyingly effective. And as Tanaka looked over the 6 Browning machine guns lying silent on the hangar floor, he realized that every other system on the Corsair was built with the same philosophy of robust, overwhelming, and systemic superiority. The devil he was discovering wasn't just in the details, It was in every single detail. The deeper Kenji Tanaka's teams delved into the Corsair's anatomy, the more they realized that the aircraft's true genius lay not in any single spectacular feature, but in the relentless systemic quality of its every component. It was a lesson in the cumulative power of small superiorities. After the engine and the armaments, they turned their attention to the seemingly mundane systems that make an aircraft function: the hydraulics, the electronics, and the cockpit environment. It was here in the hidden guts of the machine that the industrial and philosophical chasm between the two nations became most apparent. The hydraulic system was a prime example. The Corsair relied on hydraulics for several critical functions: retracting and extending its heavy landing gear, folding its wings for carrier storage, and operating its flaps. In a Japanese aircraft, the hydraulic system was often a source of weakness. The tubing was prone to leaks, the actuators were often underpowered, and the hydraulic fluid itself was of inconsistent quality. The Corsair system was on a different planet. The hydraulic lines were made of high-pressure, steel-reinforced tubing with precisely machined fittings that showed no signs of leakage. The actuators were powerful and robust-looking, more like components from a piece of heavy construction equipment than an aircraft. The entire system was designed with redundancy and fail-safes. It was clear that the designers at Vought had engineered it not just to work, but to continue working even after sustaining combat damage. Then there was the electrical system. The Corsair was powered by a 24-volt electrical system driven by a powerful engine-mounted generator. This system powered a dizzying array of equipment: the radio, the navigation lights, the cockpit instruments, the electric fuel pumps, the gun heaters, the landing lights, and the identification friend or foe IFF transmitter. When the engineers examined the wiring harness, they were stunned. It was a masterpiece of industrial organization. Thousands of feet of high-quality insulated copper wire were neatly bundled, color-coded, and routed through the airframe in protected channels. Every connection was made with a high-quality, vibration-proof connector. The junction boxes were clearly labeled, and the entire system was documented in a detailed maintenance manual that, to the Japanese engineers, was as impressive as the hardware itself. In a late-war Japanese fighter, the electrical system was often a chaotic mess of uncoded wires, a nightmare for maintenance crews, and a frequent source of in-flight failures. The Americans had turned even wiring into a weapon of reliability. But it was the cockpit that delivered the most profound psychological blow. Sitting in the pilot's seat of the Corsair, Kenji Tanaka was not in the cramped minimalist environment of a Zero. He was at the command center of a complex weapons system. The instrument panel was a vast, logically arranged array of gauges, dials, and switches, each one clearly labeled with phosphorescent paint for night operations. There were gauges for engine RPM, manifold pressure, oil temperature, cylinder head temperature, fuel pressure, hydraulic pressure, and a dozen other parameters. The pilot had a complete real-time diagnostic overview of his machine's health. The radio equipment was another shock. The Corsair was equipped with a powerful VHF very high-frequency radio, which provided clear, static-free voice communication over long distances. This allowed American pilots to coordinate their attacks with a level of precision that was impossible for Japanese pilots, who still relied on older, less reliable HF radios that were prone to interference. This superior communication was a massive tactical advantage, allowing squadrons to function as a cohesive team rather than a collection of individual fighters. American pilots could share information about enemy positions, warn each other of threats, and coordinate complex maneuvers, all with crystal clarity. The cockpit was also designed for pilot comfort and efficiency, a concept that was almost alien to Japanese design. The seat was adjustable. The rudder pedals could be moved to accommodate pilots of different heights. There was a cockpit heating and ventilation system. There was even a relief tube for long missions. These were not luxuries. They were calculated investments in pilot performance. A comfortable, less fatigued pilot is a more effective pilot. He makes better decisions, reacts faster, and can endure the rigors of a multi-hour combat mission. The Americans understood this, and they engineered the solution. As Tanaka sat in that seat, surrounded by the quiet hum of American electronics and the solid feel of American manufacturing, a wave of professional despair washed over him. He and Jiro Horikoshi had designed the Zero to be an extension of the pilot's body, a machine so light and responsive that it felt alive. It was an artist's creation. The Corsair was something else entirely. It was not an extension of the pilot. It was a powered exoskeleton, a suit of technological armor that made the man inside a Superman. It was a scientist's creation. Every component, from the engine to the wiring, from the armor to the radio, was a separate, optimized solution to a specific problem. And the sum of these parts was an aircraft that was brutally, overwhelmingly effective. It didn't matter if the Corsair lacked the delicate soul of the Zero. It didn't need a soul. It had horsepower, it had armor, and it had 50 caliber machine guns. In the brutal calculus of aerial combat in 1945, that was all that mattered. Tanaka knew now that he had seen everything he needed to see. The analysis was complete. All the data had been collected, all the components measured and tested. Now came the hardest part of his job. He had to synthesize all of this overwhelming, demoralizing information into a single, coherent document. He had to write the report that would be sent to the admirals of the Imperial Navy, the men who were still clinging to the hope of a decisive battle, of a miracle that could turn the tide of the war. He had to tell them the truth. The act of writing the report was for Kenji Tanaka a more arduous task than the months of technical analysis that preceded it. The hangar, with its familiar smells of oil and metal, had been a place of objective facts, of measurements, and material compositions. His office, spare and quiet, was a place of meaning, of inescapable conclusions. The blank pages on his desk felt heavier than any piece of the Corsair's armor. This document could not be just a dry recitation of technical specifications. The admirals would read the numbers, the horsepower, the armor thickness, the ammunition capacity, but they might not grasp the full systemic truth that those numbers represented. It was his duty as an engineer, as a patriot, to make them understand. He had to translate the language of metallurgy and aerodynamics into the language of victory and defeat. He began not with the engine or the wings, but with a philosophical premise. He wrote that the F4U Corsair was not simply a more powerful aircraft than its Japanese counterparts, but that it was the product of a fundamentally different conception of warfare. He described it as a mobile weapons platform, a system designed to deliver a pilot and a massive payload of firepower to a target with the highest possible probability of success and survival. He contrasted this with the Japanese philosophy, which he characterized as creating an aerial dueling weapon, a system designed to maximize the individual skill of a highly trained pilot in a one-on-one engagement. In 1941, the dueling weapon had been superior. In 1945, the mobile weapons platform was rendering it obsolete. He then moved to the details, using the cold hard data to build his case. He dedicated an entire section to the Pratt & Whitney R-2800 engine. He didn't just list its horsepower, he explained what that power meant in tactical terms. He described how the two-stage supercharger allowed the Corsair to dictate the altitude of engagement, forcing Japanese fighters into a defensive posture from the very start. He included charts showing the precipitous drop-off in performance of Japanese engines above 2,000 feet, compared to the R-2800's consistent power output. He wrote, "The enemy does not fight us at the altitude of our choosing. He forces us to fight at the altitude of his, where our machines are weakest and his are strongest. This initial advantage is often decisive before a shot is ever fired." Next, he addressed the issue of construction and survivability. He detailed the weight and placement of the armor, plating the bullet-resistant glass, the self-sealing fuel tanks. He included calculations showing the statistical increase in pilot survival these features provided. He knew this would be a controversial section. The tradition of the samurai, of the warrior who disdains defense in favor of pure offense, was deeply ingrained in the military culture. He had to frame it in a way they would understand. He wrote, "The Americans do not armor their aircraft because their pilots lack courage. They armor their aircraft because they view the pilot as a strategic asset, an investment of training and experience that is too valuable to be wasted. Their system is designed to conserve this asset, allowing their most skilled pilots to accumulate hundreds of hours of combat experience. Our system, by prioritizing performance above all, expends this asset at an unsustainable rate. We are losing not just pilots, but the very combat experience that is our greatest remaining advantage." Then came the section on firepower. He presented the stark, brutal numbers: 2,350 rounds of 50 caliber ammunition versus 120 rounds of 20mm cannon, a combined rate of fire of 4,800 rounds per minute. He described the quality and reliability of the Browning machine guns. He included a translated excerpt from an American gunnery manual showing the sophisticated understanding of ballistics and convergence patterns. He concluded the section with a chilling sentence: "The enemy has successfully industrialized the concept of annihilation. Their weapon system is designed not to disable, but to utterly destroy, and it possesses the logistical support to do so without restraint." He devoted the final section of his report to what he called the foundation of quality. Here, he detailed the endless examples of superior manufacturing. He and his team had witnessed the precision of the forgings, the uniformity of the rivets, the quality of the wiring, the logic of the cockpit layout. He argued that these were not minor details, but the bedrock of the Corsair's reliability and performance. He wrote, "We have been defeated not in the design studios where our concepts are often the equal of our enemies, but in the factories." The American pilot enters combat with absolute confidence in his machine, knowing that every component has been built to the highest possible standard. Our pilots enter combat with the knowledge that their engines may fail, their guns may jam, and their airframes may not withstand the stresses of battle. This is a battle of industrial philosophy, and we are losing it. He paused his pen, hovering over the page. He had laid out the facts, the cold, unforgiving logic of the situation. But the report felt incomplete. It lacked the final human element. He thought of the young skilled pilots he knew, men who went up day after day in their Zeros and Raidens against impossible odds, fighting with a courage that was almost superhuman. They deserved to have their sacrifice understood. He added a final somber paragraph. In conclusion, the F4U Corsair is the embodiment of a nation that has harnessed its full industrial capacity for war. It is a weapon that reflects their wealth, their resources, and their pragmatic approach to engineering. To face this machine is to face the full weight of the American factory. While the spirit and skill of our pilots remain unmatched, we must recognize that spirit alone cannot defeat an enemy who has mastered the mathematics of production. The war in the air has become a war of attrition, and the evidence presented by this captured aircraft proves with devastating clarity that it is a war we can no longer win. He signed his name, his hand steady. The truth was told. He sealed the report in a classified envelope. He had done his duty as an engineer. Now the admirals would have to do theirs. He knew his words would be unwelcome. They might even be seen as defeatist, but he also knew they were true. The Corsair on his hangar floor was more than just a captured prize. It was a verdict. The arrival of Kenji Tanaka's report at the headquarters of the Imperial Japanese Navy's General Staff was not a singular event. It was one more piece of a vast, grim mosaic of defeat that was taking shape in the spring of 1945. The admirals who read Tanaka's words were men who had once presided over the most powerful naval air force on the planet. They had planned the audacious strike on Pearl Harbor, had overseen the lightning conquests of Southeast Asia, and had believed with absolute conviction in the manifest destiny of the Japanese Empire. Now they were presiding over its dissolution. Tanaka's report was not read in a vacuum. It was read against the backdrop of a relentless, ever-tightening noose. It was read to the distant, percussive thunder of American B-29 seconds systematically firebombing Japan's cities into ashes. The superfortresses flying from bases in the Marianas that had been captured at a terrible cost in American blood were operating with near impunity. Japan's own interceptor force, starved of fuel parts, and experienced pilots could do little to stop them. Tanaka's description of the R-2800's two-stage supercharger was not an abstract technical detail. It was the reason American bombers could fly higher and faster than most Japanese fighters could effectively reach. The report was read by admirals who knew that the Imperial Navy itself had effectively ceased to exist as a coherent fighting force. The crushing defeat at the Battle of Leyte Gulf in October 1944 had been the final decisive blow. The super battleship Musashi, the pride of the fleet, lay at the bottom of the Sibuyan Sea. The aircraft carriers, the instruments of Japan's early victories, were either sunk or were now hiding in port without fuel, and more importantly, without the trained pilots to fly from their decks. Tanaka's analysis of the Corsair's ruggedness and survivability was a bitter pill to swallow for men who had lost thousands of skilled airmen in fragile, unprotected aircraft. The report was read by men who were grappling with the catastrophic failure of their own industrial production. The American submarine blockade had been brutally effective, strangling the flow of raw materials, oil from the Dutch East Indies, rubber from Malaya, iron ore from China, that were the lifeblood of Japan's war economy. Factories were being forced to shut down not just because of bombing, but because they had nothing to build with. Tanaka's description of America's seemingly infinite resources and flawless manufacturing quality was not a revelation. It was a confirmation of a reality they were living every day, in the form of production quotas that could never be met and equipment that failed at critical moments. The Corsair report therefore became a symbol, a microcosm of the entire unwinnable war. It took all the disparate, overwhelming problems facing the empire, the technological gap, the production disparity, the resource starvation, and concentrated them into a single undeniable artifact. You could argue with intelligence estimates. You could dismiss combat reports as exaggerated, but you could not argue with the physical object on the floor of the Yokosuka hangar. You could not argue with the spectrographic analysis of its aluminum, the Rockwell hardness of its steel, or the measured output of its engine. It was the truth rendered in metal. For some on the general staff, the report was a cause for despair. It was the final nail in the coffin of their hopes. For others, however, it paradoxically strengthened their resolve, but in a new horrific direction. If conventional victory was impossible, if they could not compete with the enemy on a technological or industrial level, then the only path remaining was to make the cost of victory so terrible for the Americans that they would lose the will to fight. If spirit could not defeat the American factory, then perhaps it could bleed the American people into a negotiated peace. This was the birth of the last desperate strategy of the Japanese Empire, the institutionalization of the kamikaze. The idea of the special attack was not new, but in the final months of the war, it became the central pillar of Japan's defense. They would hurl their remaining pilots and aircraft at the American fleet in suicide attacks, hoping to inflict such horrifying casualties that the American public would demand an end to the war. The Corsair ironically played a role in this final tragic chapter. The same ruggedness and firepower that made it a superior fighter also made it a formidable defense against kamikaze attacks. Corsair's flying combat air patrol over the fleet off Okinawa became the first line of defense, intercepting incoming suicide planes and trying to shoot them down before they could reach the ships. Their 6.50 caliber guns were often the only thing standing between a U.S. destroyer and an explosive-laden Zero. The war had come full circle. The Corsair, a machine designed with the express purpose of saving its pilot's life, was now locked in a death struggle with an enemy who had turned the pilot himself into a guided missile. It was the ultimate clash of military philosophies playing out in real time in the skies over the Ryukyu Islands. The findings in Tanaka's report were no longer academic. They were matters of life and death for thousands of sailors on the ships below. Every advantage the Corsair possessed, its speed to intercept its armor, to withstand defensive fire, its firepower to destroy, was being tested in the crucible of Japan's final fanatical defense. The engineers at Yokosuka had performed the autopsy of an enemy weapon, but in doing so, they had also written the prologue to their nation's last and most terrible act of war. In August of 1945, the war ended, not in a negotiated peace born from kamikaze attacks, but in two blinding flashes of nuclear fire over Hiroshima and Nagasaki, and the entry of the Soviet Union into the war against Japan. It was the ultimate expression of the American technological and industrial superiority that Kenji Tanaka had documented in his report. The Corsair in the Yokosuka hangar, the subject of so much intense study, became just another piece of captured enemy equipment in the chaotic aftermath of the surrender. When American occupation forces arrived at the naval base, they found a treasure trove of technical intelligence. The dissected Corsair sat alongside other captured Allied aircraft, a P-51 Mustang, a B-29 engine, and a host of Japanese prototype aircraft, including rocket-powered interceptors and jet designs that had come too late to change the course of the war. The captured Corsair itself likely met an unceremonious end. In the massive cleanup and demilitarization of Japan, it was probably scrapped its high-grade aluminum and steel, melted down and recycled, perhaps to become part of the pots, pans, and automobiles of a new peaceful Japan. Its existence as a physical object vanished, but its legacy, the lessons it had taught, would endure in the most unexpected of ways. For Kenji Tanaka and thousands of other Japanese engineers and scientists, the end of the war was not an end, but a new beginning. Under the American occupation, they were forbidden from designing and building military aircraft. Instead, they were tasked with rebuilding Japan's shattered civilian industry, and they brought the hard-won lessons from their wartime analysis with them. They had seen in the Corsair the power of a system built on quality control, standardization, and relentless data-driven improvement. They had been defeated by a nation that had mastered the art of high-quality mass production. They resolved that Japan would learn from its victor. In the 1,950 seconds and 60 seconds, the world witnessed the Japanese economic miracle. Companies like Toyota, Honda, and Sony rose from the ashes to become global industrial giants. Their success was built on a new manufacturing philosophy, one that emphasized concepts that would become famous worldwide: the Toyota production system, lean manufacturing, and total quality management. These philosophies were centered on the obsessive pursuit of quality, the elimination of defects, the empowerment of workers to ensure standards were met, and a process of continuous improvement known as Kaizen. While many factors contributed to this miracle, it is impossible not to see the ghost of the Corsair in its DNA. The Japanese engineers who had once marveled at the flawless consistency of the Corsair's rivets and the perfect tolerances of its engine components now applied that same fanatical attention to detail to the cars, motorcycles, and electronics they were building for a global market. They had learned the lesson that the Americans had taught them, that true industrial power lies not just in a brilliant design, but in the ability to execute that design perfectly millions of times over. The Corsair itself went on to a long and storied career. It served with distinction in the Korean War, not as an air superiority fighter. That role now belonged to jets like the F-86 Sabre, but as a rugged and reliable ground attack aircraft. Marine pilots flying from carriers and forward bases used the Corsair's heavy bomb and rocket load to provide close air support for troops on the ground, earning the eternal gratitude of the infantrymen they protected. It flew in colonial conflicts with the French Aéronavale in Indochina and Algeria. Its final combat missions took place in 1969, nearly 30 years after its first flight, a remarkable testament to the soundness of its original design. Today, the Corsair is a beloved icon of aviation history, a star at air shows around the world. Its thundering radial engine and distinctive bent wings thrilling crowds wherever it flies. But its most profound legacy may be the silent, invisible one. It stands as a monument to a pivotal moment in history when two great nations, locked in a struggle for survival, confronted each other not just with armies and navies, but with competing philosophies of engineering and industry. The examination of that captured fighter in a quiet hangar in Yokosuka was more than an intelligence operation. It was a moment of profound and ultimately transformative understanding. It was a lesson written not in propaganda or combat reports, but in aluminum alloys, precision forgings, and manufacturing tolerances that spoke with undeniable eloquence about the true nature of modern power. The Japanese engineers had set out to understand a machine. They ended up understanding the future. And in that understanding, they laid the groundwork for their own nation's rebirth, rising from the ashes of defeat to become an industrial superpower in their own right, armed not with weapons of war, but with the very principles of quality and production that they had first witnessed in the heart of their captured enemy.